is a good place to start. All right. So, let me just, today would be the day that I would put myself on mute. Looks like I'm okay. Okay, good. All right. So from Friday, I got you to either read 3.3, that's totally fine by me, but no fun, or watch the videos from 3.3, but I'll give you credit where credit is due.
What if you don't deserve any credit?
Then the credit is on credit. You covered section 3.3 on your own. Yee, good job. It's okay, we're not gonna rely on it today, but if you did go down that route, then you know that finding horizontal asymptotes, finding vertical asymptotes, all that fun stuff, you know how to do that for any polynomial, not just the quadratic. And I bet you thought at some point, man, I wish I could do long division of polynomials. At some point, surely. Well, guess what? Today we're doing long division of polynomials. I know. So, we saw how much easier it is to work with polynomials that have been factored. But I don't know about you, I'm terrible at factoring. I don't see it, right? Things like, oh, it has to add to B and multiply to C. Those don't pop out at me. I have a really hard time with factoring. And so, and that's, I've survived this long, so it's fine. But it is hard, right? And so what we're going to introduce today is long division of polynomials. So let's see here. What we're leading into is called the factor and remainder theorem, which are going to be pretty obvious once you see them. Just you won't believe what happens next. Number 13 blew my mind. Hey, why isn't it letting me copy it? Copy. Let's see here. So just stealing from textbook because I don't want to write. Oi, oh my gosh, what a day. It's shaping up to be there. So if we factor a polynomial, right, then we can write something like x to the power of 3 plus 4x squared minus 5x minus 14. Let's say if we knew that x equals 2 was an intercept, right, that's something that we were given, then one of the things that we can do is we can rewrite this polynomial as x minus 2, because if x equals 2 is an intercept, a horizontal intercept, then of course x minus 2 must be a factor, right? I can pull it out, and if x equals 2 here, then I get 0, so then the output is 0, which is what happens on, let's just do a little refresh here. Here is when f of x is equal to 0. So at some point, x equal to 2, we know that it crosses the x-axis. And so then what we say is then x minus 2 times something tells me that x equals 2 is a horizontal intercept. I'll just write HI. Yeah. Because if I plug in x equal to 2 here, this goes to 0, right? Let's see here. 2 minus 2 times anything is equal to 0, right? Which is what satisfies it, right? And so that's why having it all factored makes it easier to find the horizontal intercepts, right? And so what we want to do today is just kind of figure out a way that we can pull out an x minus 2 from some polynomial, which means long division. And kind of a funny thing. So I never learned long division in school because, well, we moved back and forth between Sweden and here. And so I skipped half of grade 1 and went straight into grade 3 here. And then I did grade 3, 4 here. And then we moved back and I did grade 4 again because they're to be with the same age group. And then I did 4 and 5 in Sweden. And then we moved back. So then I skipped grade 6, which is when you learn long division. Went straight into grade 7. Never needed long division. I have a math degree. I have a master's in stats. Never once did I need long division, which is crazy. Until I had to teach it. It's like, what? What is this? What is this? I get it, but kind of funny to make my way through my academic career without knowing it. But it's super fun. You just have to be methodical, right? And super careful, okay? So let's see here. Let's see. Oh, okay. Let's just snag the one that we were talking about then. Come on. So slow. Okay, so to find the something, right? This something, oh, that doesn't look like an arrow. There. We need to divide. We need to divide x to the 3 plus 4x squared minus 5x minus 14 by x minus 2. So that's going to look a little something like this. X minus 2, flashbacks to long division. You've got a little curly brace, or whatever you want to call it, is going to divide into x to the 3, 4x squared, 5x minus 5x minus 14. And one of the things that I want to make a note of is if you have a 0 coefficient, right? For example, this 5x was missing, right? Then I would still write out the plus 0x, right? And so that you have all your powers of x, because they're going to be placeholders. Okay, so that's my first note, I guess. If there are missing powers of x, include them. That might not make sense until we do an example of that. But for now, we have all of them. X to the 3, x to the 2, x to the 1, x to the 0, right? They're all there. Oh, let's see if I can remember. That's not a good feeling, is it? Well, imagine being me. Long division under pressure. No, it's fine. 4x squared minus 5x minus 14. Okay. I had to make room because I need to be able to put things up top here. Okay. So now what I want you to remember is that this is an x to the 3 column, this is an x to the 2 column, this is an x to the 1 column, and this is the x to the 0 column. Okay. So what we're going to do is we're going to take the leading term, I guess, and which is x in this case, and we're going to divide it into the first term, okay, the leading term of the original polynomial. Okay, so we have x to the 3 divided by x, which gives me x to the 2. Nice. Okay, let's see here. X to the 3. Step number 1, x to the 3 divided by x is x squared, which is why I put it there. I want to kind of keep notes. Oh, I rolled the blinds up because I thought it was so dark in here, but now I'm racing against daylight. Okay, so notice how I put the x to the 2 above the x to the 2, right? Because are we going to have an x to the 3 here? No, right? Because if I'm taking something to the power of 3 and dividing it by 1, the highest power that I'm going to be left with is x to the 2. Hey, thank you. Okay, so now what we're going to do is we're going to take this x to the 2 and you're going to multiply it by x minus 2. Okay, and where you're going to put those are below here. Okay? Keeping your powers stacked on top of each other because eventually we're going to subtract them. Okay, and so that was step 1. Let's see here. Thank you. Step 2 is going to be x squared times x minus 2, using that green to show that that's where it's from. And I get x to the 3 minus 2x squared. Okay. So I'm going to put that x to the 3 minus 2x squared. Oh. The third thing we're going to do is subtract from the original. Which is going to look like this. Whee! Okay. So now, let me see if I can move my pen there. Phew. Can't see it. So now I have x to the 3 minus x to the 3, and you're welcome to expand this minus inside, right? Or just keep track of, okay, this is minus x to the 3, but then plus 2x squared. All right. Okay, so now I get x to the 3 minus x to the 3. Nice. 0. Right. So I'm slowly going to be chipping away at these powers of x. Right? And if the leading term that you're working on doesn't go to 0, something went wrong. Okay. And so x to the 3 minus x to the 3, that's good. And then 4x squared, hey, 4x squared minus negative 2x squared is 4x squared plus 2x squared, which puts me at plus 6x squared. I'm going to run out of colors here. Or you can bring these guys down. Those are unaffected. Or you can keep them up there, but I like to write them out so then I can just focus on the terms down here and I don't have to be jumping around, right? And so now I'm going to bring down the other terms. So I get minus 5x minus 14. And now this is my new polynomial that I'm going to divide into. And guess what? We just do it all over again, right? What's going to happen? We're going to chip away at this x squared. It's going to become an x, right? And then we're going to have an x squared. We're going to subtract. They're going to go away. And slowly but surely, we're going to chip away at this thing. Yeah. And so now we start over. And I've got a page break. Ill-timed page break. Oh boy. Okay. I guess it is what it is. So now we're going to start over. So now I have 6x squared. What did we do before? We divided by x, right? So now I'm going to do 6x squared divided by x, which puts me at 6. Can I call it 1 again? Sorry. 5. 6x squared divided by x is 6x. So now I have plus 6x. Step 6 is going to be 6x times x minus 2 again, which is 6x squared. Phew, why? Because I want to cancel that 6x squared, right? And so 6x squared minus 12x. Okay. Being really careful with your negatives since we're going to be subtracting, and it would make a real mess if you missed a negative. And that's more of a note to myself than anything else. Don't screw this up, Emily. All right, so now I have 6x squared minus 12x that I can put here. 6x squared minus 12x, which, oh, not yet. I have to subtract from 6x squared minus 5x minus 14. It's going to be across the page here. Might look a little weird. But I get 6x squared minus 6x squared, so that's good. I'm at 0, right? Just a check-in point. And then I have to deal with negative 5x plus 12x is what? 7 plus 7x? Phew. Okay. Now I can bring down that 14 or the minus 14. Bring down minus 14 here. And now we start over. Like I said, as long as you're methodical about it, nice and slow, then it's really fun, I think. I know. Okay. Starting over, 7x divided by x leaves me with plus 7. Okay. Maybe I'll put it over here. 7x divided by x is 7. So I get plus 7. then I've been using orange. Orange, you glad? Then I get 7 times x minus 2 is 7x minus 14. Haha. Looks good, right? 7x minus 14 minus 7x minus 14. Feeling like I'm onto something. Subtract from 7x minus 14. Okay. Yeah, I forgot to write it down. 7x minus 14. Oops. Subtract that. 7x minus 7x puts me at 0. That's good. Negative 14 plus 14 also puts me at 0. We're all out of terms. And we're done. So therefore, x to the 3 plus 4x squared minus 5x minus 14 is x minus 2 times whatever we had up top here, times x squared plus 6x plus 7. That's the something. That's still not factored, but it's a quadratic. So what can we do? We can use the quadratic formula to find the factors or the horizontal intercepts of this quadratic, right? And so here, I want to use a color that I haven't used yet, right? So here, this is a quadratic. To find the horizontal intercepts of a quadratic, right? Let's say I wanted to keep factoring this, right? Or at least try. How do I use the quadratic formula to do that? Quadratic formula says that if I set this equal to 0, which is what I want to do, right? If I'm trying to find the horizontal intercepts, well, then I get x is equal to negative b plus minus the square root of b squared minus 4ac all divided by 2a. In this case, a is 1, b is 6, and c is 7. Right? So I can use this formula to find the x values that make this 0, right? Okay, so I have negative 6 plus minus the square root of 6 squared minus 4 times 1 times 7 divided by 2 times 1. I need my calculator. Can't do this on my own. Or it would take too long. 6 squared is 36 minus 4 times 7, which is 8. It's not going to be a nice number, is it? Negative 6 plus minus the square root of 8 divided by 2. Now the square root of 8, I can rewrite as the square root of 4 times the square root of 2. Shouldn't have this. Or your calculator might do it for you. I can't remember if that's what it wasn't doing, your new fancy one. If you do the square root of 8 on your calculator, does it convert it to 2 root 2 or does it just keep it as root 8? Converts it to 2 root 2?
Put it back so you can look at it.
Oh, good.
It was just
So what's the trick?
It was in the setup. So
Okay.
just regulate this in your mouth. So it goes.
Yeah, so if we do the square root of 8. Nice. Okay.
If I put it in the 2 mode, it would give me fractions.
Did everyone else get it set up to, so's shift set up? Here, do you mind if I try to
On the, yeah, here.
recreate the magic?
Mine's set up
Similar, but
now.
okay. How are we gonna do this? Oh, it doesn't like it because I'm projecting, I guess. Okay, let's see here. I just need a picture of it. Come on. Did it take it?
What is it?
It's not showing up in my. Okay, let's do this. Use photo. Okay, rocking and rolling. Now I have it. And okay. So is shift setup. And then 1, right, for the math menu. And then it was 1 again for math O. Can't tell if it's an O or a 0. To have your calculator simplify expressions such as the root of 8 is 2 times root 2. Right? Otherwise, what would you have to do? You would have to say, okay, well, I can rewrite 8 as 4 times 2. That's fair. If I'm multiplying inside the square root, I can break it up and say that's the same thing as root 4 times root 2, but the root of 4 is 2, and the root of 2 is just root 2. It's nothing nice. So you can do it by yourself or have your calculator do it. Might be nice, right? I just let my calculator do all my simplifying. So that's why if it looks like I've made a huge leap, a huge mistake, no, but a huge leap, then I've just let my calculator take the reins. So then, how can I continue this? X is -6 plus minus 2 root 2 divided by 2. Of course, I can rewrite -6 as 2 times -3, and I can cancel the 2's all around, right? I'm only allowed to cancel this 2 if I can do it from each of the terms, right? If they're adding or subtracting up here, right? So I can ding, 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 and I get X is -3 plus minus root 2. Not a nice root, right? But a root with a root, square root. -3 plus, or maybe I'll do the minus first. Minus root 2 or -3 plus root 2. those are my other roots. Okay. And so let's see if can my calculator hack it / yours. -3 plus √2. Let's try that. No, it doesn't want to do anything. It's a number, right? So we can just wrap it up in brackets. Maybe I'll do, yeah, that's fine. What was our goal? Rewrite this as something factored, right? And so here I'm gonna snag this again, copy, but I don't want to write it out. Paste. Okay. These are just numbers. So I get x plus -3 minus √2, right? Is that right? Times x. I'm going to go plus again, I think. I am going to confirm it with Desmos because the issue might be that it's minus here. X minus. It is minus, I think. It's a nasty root. Okay. Just so we have a handle on this, what are these approximately? -3 minus √2 is roughly -4.414. And -3 plus √2 is approximately -1.586. So you could write those values here, right? Instead of the exact values, right? When you keep the roots, the square roots, then you have the exact value, right? As soon as you've converted to decimal places and done some rounding potentially, then you have approximations. Okay, let's see here. And will it show me? Will it show you? It shows me. Nice. Sometimes I do that and it doesn't show you. Depends on the room we're in, I think. But what do I want to do? I want to take this huge thing. I want to start with the original. And then I'm going to confirm that x minus 2 is one of the horizontal intercepts. And these two little nasties. Okay. X to the 3 plus 4x squared minus 5x minus 14. Okay, so now, oh, that's not what I wanted to do there. Wow. But Emily, couldn't we just have used Desmos this whole time? Yes. But isn't it empowering to know that you don't have to? So, did I get the values right? That's the real question. Is it plus or is it minus?
I have a question on that too.
Yes.
I kind of just got lost on that little bit where you put x.
Oh, this one here.
The very bottom, the very last bit.
This one here.
Or
Yeah.
that whole thing, or-
Here.
no, right
Here.
where you were, that whole thing, what? Is that just spoiled?
So what it is we found that the roots are -4 let's call it -4 and -1.5 for simplicity's sake, right? They are these kind of nasty irrational numbers, but that's fine. Okay, and so -4 is one of the horizontal intercepts. And so what we need to do is we need to say, okay, well, when I'm factoring here, if I put in x equals -4, then the term has to go to 0. Okay, and so here, if I have x minus -4, then if x is -4, then I have -4 minus -4, which is 0. So you have to do kind of the opposite of what the root is. Kind of sneaky. It'd be nicer if this was just a nice number, right? Something tells me we weren't meant to keep going from the something into something more factored, but we can because we have the quadratic. So we did. Okay, but here what we're saying is that if x is equal to -3 minus √2, or roughly -4.414, this whole thing is equal to 0. Okay. Yeah, something tells me that was a little bit nastier than we wanted to work with for our first example. Kind of our second example, first part was long division. That's feeling a little easy now, I think, compared to this. You know? Okay, as long as you kind of close your eyes and see this whole chunk as one number, it is just a number, and you're welcome to use the decimal approximations they do here, right? And so then just confirm with yourself that if I let x be one of these terms, right, then the overall equation has to be 0. So if one of these goes to 0, it doesn't matter what I'm multiplying by, it goes to 0. See it? Yeah, you just gotta squint and don't look at the -3 plus √2 too much, because it's too nasty. Okay. Okay, nice. But we were able to find the factored form, even though there's no way you would have come up with this. And if you did, that's nuts. Just by looking at this quadratic, just by looking at this, oh, what adds to 6 and multiplies to 7? Oh, well, of course, it's -3 plus minus √2. No. Right, and so so then you have the quadratic formula that will never fail you. In fact, I use as soon as I have a quadratic, I might have an idea of what it factors into, but I just always use the quadratic formula because it will never fail me. All right, it's a little bit longer, but it'll get you there. Okay, good, sneaky. Maybe it's time for the factor and remainder theorem. Come on. Hey, they did do it. Okay, so let's grab this first. So when we did our long division, we didn't end up with any remainder, but we could, right? Just like you might have some remainder if you're doing regular long division, which if you force me to do it now, I guess I could probably fumble my way through it. but I don't actually know how. I'm better at polynomial long division. It's kind of funny. So if we divide some polynomial p of x by d of x, what's that going to look like? That's going to look like d of x is going into p of x. Okay. Then we're going to get some quotient polynomial here. That's going to be q of x up top. And then the remainder is, if it doesn't go to 0 and 0 at the very end, right? Once you run out of x's to divide by, then you're going to have some r of x down here, right? In our first example, we found that, and I'll do like ... because there's a lot of action in between, right? But what we found was that the remainder was 0 plus 0, so there was no remainder, right? D of x divided nicely into p of x and gave us q of x. And so we can rewrite this as p of x is d of x times q of x, which is what we did, right? We said if d of x is x minus 2, then I can find x minus 2 times, and then it was that nasty quadratic that we worked on, plus 0. Okay? So this is just another way of writing out this equation, but what we're still going to be doing is we're going to take d of x and divide it into p of x and find q of x and potentially r of x. Why does that matter? Well, let's see here. Do I want that first part? Nah, I'll just do this. The remainder theorem. The remainder theorem sounds important, kind of, but it's also kind of straightforward. So if p of x is a polynomial of degree 1 or greater, okay, so you have to have a polynomial to start with. So there has to be some x, right? And c is a real number. Then when p of x is divided by x minus c, so notice that this is only the case for this very, very special case, right? Just x minus some constant, which is what we did, right? We did x minus 2, okay? But this also means that that's as high as I'm gonna go. I'm gonna make you divide by x minus some constant. I'm not gonna make you divide by something crazy, like another bigger polynomial, right? We're gonna stick to x minus c, x minus a constant, for example, x minus 2, right? Which is what we did. Then what's kind of cool is that the remainder is going to be the original polynomial evaluated at c. Okay? That's crazy, right? But let's see here. Let's try it. Should we try it with ours? Our polynomial, which was this little guy. I'll use this nicer, cleaner version. I'll write a note first. We found that this p of x, right? So just to match the terms with what we're saying up above, if we divide it by x minus 2, which is x minus c, then c is equal to 2. We found that the remainder was 0, right? And so here we found the remainder was 0, right? r of x is equal to 0, right? In terms of, I guess they don't introduce it here. But what we can do is we can confirm it by taking p at 2. Okay? And so now, if we take p at 2, this is the same thing as 2 to the power of 3 plus 4, whoops, wrote x, times 2 squared minus 5 times 2 minus 14. Let's see here. 2 to the power of 3 is still 8, feels good. 4 times 4 is 16, minus 10 minus 14, whoops, 114, that'll make a mess. 8 plus 16 minus 10 minus 14, 0. It's really just a way of confirming the remainder, or if you're only interested in the remainder, that can happen. Okay. Then if you know that x minus 2, for example, or any x minus c is a divisor of p of x, then you know that if I evaluate p of x at c, right, p of c, then I get the remainder. So here, this is p of c, and this is r of x. Oh, good. So that's the remainder theorem. It's kind of fun. It's weird, but it's also a learning outcome of the course for some reason. So we have to talk about it. Okay, so then we move on to the factor theorem, which goes a little something like this. If p of x is a non-zero polynomial, then the real number c is a 0 of p of x if and only if x minus c is a factor of p of x. I think that's pretty obvious, but there's a theorem for it. Okay? And so we saw that we were able to take x minus 2, and 2 was a 0, which means a horizontal intercept, right? Maybe that needs a little reminder, right? A 0 is a root, is a horizontal intercept. That might help. But it's only going to be a horizontal intercept if x minus c is a factor of p of x. And so if you can extract an x minus c, then it's going to be a horizontal intercept at c. Okay. Now, long division is fun, but sneaky sometimes. There is such a thing as synthetic division. And if you want, you can go through and you can read about synthetic division. They walk you through, and it's just a way of condensing the long division into something like this. Okay. Because I don't want to cloud your minds, and I would prefer to just work on the long division, I'm going to leave this to you. If you want to, on the test, for example, if you want to use synthetic division, that's totally fine. But it's up to you to learn it on your own. If you want to, you're still doing the same math. It just kind of compresses it, removes all the x's, and then you put them back in. It's nothing crazy. But let's do this one with long division. I have to grab them from the textbook because if I try to make up my own polynomial with its own factor, I'll make a real mess. I know. I'll pull something that's not a factor. Could be anything. Okay. So here, let's see here. Use long division. To divide 5x to the 3 minus 2x squared plus 1 by x minus 3. Now, this is one of those scenarios where what we have to do first is rewrite this with all the coefficients of x, right? Because the coefficient x to the 1 is missing, right? And so first thing we need to do is we need to rewrite this as 5x to the 3 minus 2x squared plus 0x plus 1, right? So here, you have to fill it out with the missing coefficient. It is just 0, right? And so 0 times x, that's why it's not written, right? But x to the power of 1 has to be there because it has to be in that space. Okay. Now, I think that I should give you a moment to try and do it on your own. What are you trying to do? What are you trying to do? X minus 3 dividing into 5x to the 3 minus 2x squared plus 0x plus 1. Enjoy. It's been on Frank's desk forever. I was like, how do I know when you're done? Can't tell. Or done enough. put you out of your misery. No, it's fun though, right? Okay. I'm not going to write out the steps this time because you have them already and they're going to be the same. But what do we have to do? 5x to the 3 divided by x puts me at 5x squared, right? Stacking it on top of my x squared column. Now what do I have to do? I have to take 5x squared times x minus 3. And so now I have 5x squared times x, which is 5x to the 3. And then 5x squared times negative 3 puts me at negative 15x squared. Next thing I want to do is I want to subtract that from what's above. 5x to the 3 minus 5x to the 3, that's going to go to 0. That's nice. Negative 2x squared plus 15x squared puts me at plus 13x squared. Right? Phew. Then you can leave them up here, but like I said, I like to bring them down. As long as you don't forget about these terms, right? You still have to work them. And so I like to bring them down, but it's optional. But then I have my new polynomial that I'm dividing into, right? And let's see here, 13x squared divided by x puts me at plus 13x. 13x, so now I bounce back. 13x times x minus 3 puts me at 13x squared minus, what's 13? Negative 3 times 13 minus, I get 39x. Does that match? Yeah. Whew. Math, am I right? Then I want to subtract that. 13x squared minus 13x squared, that goes away. And then this is why it's so important to have this 0x, right? Because you need to add 39x to 0x. And so now 39x appears. And you can bring this plus 1 down. Home stretch here. Why? Because I only have the 1x left. And so I'm going to run out of terms here, and whatever is left over is going to be the remainder, if there's anything left over. So now I have 39x divided by x, putting me at plus 39. 39 times x minus 3 puts me at 39x. 39 times negative 3, it's getting out of control, minus 117. But I'm subtracting this, and how can I put this all on one page here? Bless you. I get 39x minus 39x, and then so that goes to 0, and then 1 minus negative 117, which puts me at 118, which is the remainder. Okay. All right. By the remainder theorem, right? What should we get if I plug in x equals 3, right? X equals c. X equals 3 in here. I should get 118 if I did it right, right? So here's hoping. By the remainder theorem, P of 3, which is going to be, let me just copy this. I'll do P of x and then P of 3. 5 times 3 to the 3 minus 2 times, whoops, 3 squared plus 0 times 3 plus 1. Oops. 27 times 5 is 135. 9 times 2 minus 18 plus 0 plus 1. So we did get the right remainder. Feels good. Right. So therefore, the remainder is 118. So what does that mean? That means we can rewrite this polynomial, right? We can say that P of x is equal to d of x times q of x plus r of x, where in our case, let me center this, because P of x is actually quite large. And is it still in my, if I paste it? Yeah. That's my P of x. It's not on the line there. The divisor of x was x minus 3, right? That's this little guy here, right? X minus 3. And so I can rewrite this as x minus 3. And then the quotient was what we found up top, which is 5x squared plus 13x plus 39. I don't see a nice way of factoring this, but we can use the quadratic formula because it's a quadratic to find the zeros, but I don't feel like it. So I'm just going to write this and then plus 118. All right. I'll just make a note here that this is a quadratic. Let me see, is it going to have a nasty square root again? How can I check? If I do b squared minus 4ac, if it's not a square rootable thing, then it's going to be nasty. So I'll do 13 squared minus 4 times 5 times 39. Negative. Uh-oh, what's that mean? There's no solutions. Huh. Okay. Probably a reason we don't go down that rabbit hole. But what does that mean? It means that there are no roots. Okay, fine. Let's do the quadratic. Let's see it. Let's see it in action. Okay. 5x squared plus 13x plus 39 is equal to 0 when x is equal to negative b plus minus the square root of b squared minus 4ac divided by 2a. negative 13 plus minus 13 squared minus 4 times 5 times 39. Doesn't matter what's in the bottom, but put it there. Anyways, put her there. So if I do, let me just confirm, 13 squared minus 4 times 5 times 39. Can usually tell I'm in trouble when there's no negative term here turning this into a positive, right? Because we know we can't take the square root of a negative number. And so then there would be no solutions, which is fine. And so I get x is negative 13 plus minus the square root of negative 611 divided by 10. I'll do it in red. Can't take the root. Okay, fine. I wasn't going to say the even root. It doesn't just apply to the square root, but usually we talk about the square root, but any even root. We can't take any even root of a negative. Therefore, no solutions. Huh. What would that look like? It could just look like, well, let's have a look here. My leading coefficient is positive, so it's facing up. I have a parabola, right? And so it's facing up. And what could happen? Well, if there's no solutions, I might just have something like this. That's fine. It never crosses the x-axis. And so that's all it's telling us, right? When there are no solutions, that's totally fine. It would just potentially look something like this, right? Never crosses the x-axis. That's allowed. What does that mean for our polynomial? Our little polynomial. It means that x minus 3 is the only factor, right? And so let's have a graph, right? I know the general shape of x to the 3, right? And so I'm trying to find where it might cross the x-axis, and let's see here. Oh, no, wrong one. Five x to the 3, step it down, minus 2x squared. I'll skip the plus 0. Hey, now you can't see it? That's so confusing. I've got the split screen again. I didn't do anything different. It's on the other side. No, that can't be it. Let me try. Oh, that's crazy. So if I put it on the left, I'm showing it to you. If I put it on the right, I'm not showing it to you. That's weird, right? It's bizarro. And I just finished saying I wasn't going to do the plus 0 term, but what the hey? Ta-da. Okay. So now, okay, that's enough of that. That's not 3, is it? Why? That dang remainder, right? We have to account for the remainder, but we can tell that there's only going to be one horizontal intercept. And so let me screenshot this here. Cropped up. Like that. Okay. And so here, what we decided was that this portion can never be 0, right? And so no matter what we do, that's never going to go to 0. Our only hope is x minus 3. We can make that go to 0 or go to what? Minus 18. I want the overall thing to be 0, but then I'm dealing with these guys and too much. I don't want to do that, right? But this is our hint that there's only going to be one horizontal intercept, right? And then Desmos tells us what it is, right? And I don't want to do any more. I don't want it. Okay. Should we touch on the factor theorem again? I feel like, what was it? Well, I guess we just did. 3 is not a factor, or x minus 3 is a factor, but with the remainder, right? X equals 3 or c equals 3 is not a root, but it tells us that there's only one root. Okay. Now, let's see here. There was kind of a cheeky example in here. And by example, I mean exercise. Oops. I just finished saying, well, not just, but maybe an hour ago, I said, don't worry about a thing. We're only going to be doing division by x minus some constant, right? And here we have x squared. You can handle it, right? You can do the same thing that we did before, just dividing by x squared. Or what's another thing that you could do to tackle this, right? You could say our trusty factor theorem, right? If we have x squared plus 4, then I could maybe rewrite this as x has to add to 0 and multiply to plus 4. Right? I wanted to do x minus 2 times x plus 2, but I don't think that's going to work. Right? Negative. No, it's not. Sneaky. It is. I got to FOIL this. X squared plus 2x minus 2x minus 4. Dang. Fine. What I wanted you to do is this. Ding. That's what I wanted to show you. Just change it to be something that I like. Yeah. Well, the square root won't translate over addition or subtraction. It only translates over multiplication or division. So we can't do that, but I'm happy with my change. X minus 2 and x plus 2. I'll leave it with you to work on, but what would you have to do? You could do this division first, right? Parking lot this x plus 2 and say, first I'm going to pull out x minus 2 or x plus 2 if you prefer, right? From this thing. And then you're going to have a quotient, which you can divide by x plus 2, right? And maybe because I changed it, I've made a total mess. But I wanted to show you where you can work with two two factors or two quotients or divisors at the same time. So I'll do a run through of that before I try to do it with only a minute remaining. You can try it on your own, but if I made a total mess, then don't worry about it. All right. If you have any questions, let me know. Otherwise, I'll see you on Wednesday.